So I've been having a few problems with Zoom, and class got cut off kind of early last time, and I lost time the previous class as well. So I think what I'm going to do is have you watch this video, and this will sort of get us through what I was hoping to cover by the end of class in the first week of school. So it'd be great if you could watch this video. You should watch this video before you come to class on September 9th, which is Wednesday, because Monday's a holiday. We won't be having lecture, we won't be having lab. Now, the stuff that I'm talking about in this video is talked about in that sheet that's posted on Blackboard that says Calculus Review. And it's not necessarily review because a lot of you, of course, haven't had Calc 3. You're not supposed to have Calc 3. And so, you know, some of the ideas early on in that sheet are review, but don't worry if you don't understand it. Just try to get what you can out of reading it and then watch this video. Okay, so last time I talked about a little bit about functions of more than one variable. So for example, I talked about how a function of two variables, f of x, y, can be thought of as a surface. So above the xy plane, you know, every point on the xy plane has a point, say, above it, and that would be the value of the function, and you put all those points together and you get a nice surface. That's if they're all positive. They're not necessarily going to be all positive, but that's a nice way to visualize. But then when you have a surface, okay, then you have two distinct directions, the x and the y, and you have a slope in the x direction and you have a slope in the y direction. So you have two different slopes. And I mentioned this, talked about this in class. One of them would be called the partial derivative, or I should say, yes, the slope in one direction would be called the partial derivative with respect to x. That would be the slope in the x direction. And then the partial derivative with respect to y is the slope in the y direction. Okay, and we did some examples of finding these partial derivatives. So for this video, I'm going to focus on applying calculus or some aspects of calculus to physical chemistry, okay? And in physical chemistry, we have a somewhat different focus than in math class. So here's the thing about PChem and math, okay? So when you have a math class, you always know what the function is. You know, they tell you what the function is and you take the derivative, you use that derivative to solve different kinds of problems perhaps. But, you know, maybe you're integrating a function between two limits, but the function is known. It's not an unknown. Right now in PChem, it's really quite different, okay? We often don't have, in fact, most of the time, we don't have a formula for the function that we're interested in. For example, the Gibbs free energy, G, the enthalpy, H, the internal energy, U. Most of the time, we don't know what the functional form is for these things, or it's too complicated or something. But the thing is that we're not mathematicians, you know, we're physical chemists, okay? And we really don't care about the value of these functions. We care about the changes to these functions, okay? We care about delta G, delta H, delta U. We care very deeply about those. So how can we use calculus to figure out changes in functions, right? So we're really not, you don't need to know the formula of function necessarily. So we know how to calculate a derivative or even a partial derivative, you know, a slope, the change in the function with respect to x, the change in the function with respect to y. But how do we find the change in the function df or delta f, the change in the function f? So that's what I'm going to be talking about in this video. And I'm going to use OneNote and share my screen. Okay, so suppose, you know, so what this is all about is figuring out the change in a function. So can we get the change in a function, let's call the function f. Okay, so can we get the change in f by not knowing what the actual value of the function is? So can we get this from knowing the value of f at one point. Let's call that point x1. So we know f of x1, okay? So if we know f of x1, can we get the change in the function from knowing the value of f at one point and the derivative at that point, which is df dx at x equals x1, okay? So that's more like along the lines of how we would use calculus in PChem, okay? We would like to know, can we figure out the change in a function? We will, later on we'll be interested in changes in enthalpy and things like that. Can we figure out what it is as long as we know the derivatives, okay? So for a one-dimensional function, we only have one derivative. So let me start with a very easy example, the easiest example. And that is a linear function. Okay, so suppose I have a linear function. So if it's a linear function, I know f of x is mx plus b, and I could also call this y. A lot of times we say y equals f of x. And the value of the function at x1 is y1. And the value of the function at x2 is y2, but I don't know this. I want to predict this. So let's figure out what would the change in y be, the delta y, or y2 minus y1. Now we have a linear function, okay? So y equals mx plus b. So that means that y2 is the slope m times x2 plus b. And then we subtract the slope times x1 plus b. And so we get mx2 plus b minus mx1 minus b. The intercepts cancel. And this becomes mx2 minus x1. So we really haven't done anything too interesting here, right? I've just showed you that delta y, the change in y, which by the way is also the change in f, the change in the function, is the slope times the change in x. So there's nothing really earth-shattering over here, okay? We know that the change in the function should be the slope times the increment in x. Okay, this makes total sense because for a line, we know, so the slope we know is the change in y over the change in x. We know this from, high school, okay? So if you take the slope times the change in x, that's just delta y over delta x times delta x, which guess what? It equals delta y. So there's nothing new here, really. So what we're saying then is that we can take and figure out the change in y by taking delta y over delta x times delta x, okay? But now, here's the thing about linear functions. Linear functions, they have a slope, but they only have one slope. So the slope here is the same as the slope here. The slope is the same everywhere. That means that this delta y, delta x at x1, if this is x1 and you have your delta y over delta x, right? Okay, that's actually equal to the derivative dy dx. And that derivative is constant. So delta y equals dy dx delta x anywhere for a linear function. And that's because this dy dx doesn't change. So whatever delta x you have, you multiply by the slope, which is really the same everywhere. That gives you the change in y. So you can definitely, for a linear function, use the slope dy dx, which is the same everywhere. So you could definitely use the slope at x1, because that's a point that's one of the everywheres, and multiply by the change in x to get the function at, to get the change in the function, to get delta y or delta f, okay? So you can always do that. This is always going to be valid. Delta y is always going to be df dx delta x for a linear function. So I'd like to just show you graphically what I mean by this, okay? So here is a set of axes, okay, and here's a nice line. And here is my point x1. It's right here, okay? So for a line, if you multiply the slope, I have the slope right there. The slope right there is dy dx, right there, at x1. If I take dy dx and multiply it by delta x, and really it's the same as delta y over delta x times delta x, what it's going to do is it's going to give you, and you take the delta x to be x2 minus x1, it will tell you what this difference is. It will give you delta y, and it will always be on the line. It'll always work. So now you have basically predicted, you have gotten the delta f, so now you know what f of x2 is, because all you have to do is take f of x1 and add that delta f, and that gives you f of x2. So this always works for a line. You can always predict what the change in the function is going to be from the derivative. So does this work for all functions? So what if you have a function that is not linear? Will this work for a non-linear function? Okay, so I have a nice non-linear function here in this next diagram. Very non-linear, right? This is the function here. It's making a nice big curve. Okay, and here's a value of x1 right here. And this is f of x1. So if I take the slope at x1, so df dx at x equals x1, and I multiply that slope by the change in x here, df dx at x equals x1, I'm not going to write that again, times delta x, it's going to predict a value of the change in the function. What value does it predict? Well, it's this slope, it's going to take and basically take the line defined by that slope here, the red line, and it's going to use that line to predict the value of the function at x2. Okay, it's going to predict the value of that function at x2. And it's going to be really off, right? Because this slope here at x1 is not the same as the slope all along this line. The slope is constantly changing. So it's going to over-predict. It overshoots, right? If the function had a different shape, it might undershoot it. But it overshoots the true value of the change in the function. So this is the value of the change in the function that it predicts. But this here is the actual change in the function. This is the change in the function here, this small red arrow. So this is way too large a change in f is predicted. So, why does that happen and what can you do about it? Okay, so I'm going to write delta f is not equal to df dx delta x for a nonlinear function. So how could I change this? How could I change this formula? I have this formula here. How could I change it to make it right? Okay, well, the reason why it's wrong is because I have this big delta x here. I have delta x that's over a significant range, and in that range of x's, I have many different slopes. So if I could look at this in the limit as I keep decreasing that delta x, keep making that delta x smaller and smaller, okay? So if I could look at this in the limit as delta x approaches 0, this will be correct, or it will approach the correct answer. Oops. So it basically means I take this formula and I have to change it a little bit. I have to make it that the infinitesimal change in the function equals the derivative times the infinitesimal change in x. So that means I can take my derivative at x1, right, multiply it by an infinitesimal change in x, and I'll get an infinitesimal change in y. And this is correct. Okay, so that is a very important formula. It seems really stupid, right? Because it seems like, oh, you just cancel the dx's, right? Cancel the dx's and you have df equals df. So couldn't I have written this, you know, from the beginning? But would you have understood it? I hope that this helps you understand what this is a little bit, that you could predict a change in a function by taking a derivative and multiplying it by the change in x. You could predict what the change in f is for the next x. Okay. All right. So how do we apply this to more than one variable? Okay, so here's our nice picture of the surface again. And so now, if we're going to change the value of x, maybe we're going to change the value of x and the value of y. So here's the x-axis in this direction. If I change the value of x, then I'm kind of moving along this curve. If I increase the value of x, right, I'm going to go in this direction along the curve. And that is going to produce a certain change in the height, which means a certain change in the function. So I'm going to get a delta f from changing x. But now I'm going to change y a little bit. So I'm going to go a little bit in this direction. But as I do, I'm going to have to follow the slope in that direction. Draw that a little better. I'll use a different color. Okay, so this is delta f, or I should, let me call, well, there, for changing y. So I have to add, must add the changes in f that come about by changing x and changing y. And each of them have a formula like df is df dx dx. We have df is df d. Now they're partial derivatives, right? Because there's two variables. So this is basically what I had before. The change in the function is the derivative with respect to x times the change in x. And that's exact as long as dx is an infinitesimal for any type of function, linear or not. But now I have to do the same thing. Okay, so this df dx here represents the slope of the black curve that I've drawn up here. Okay, and this represents the slope of the red curve that I've drawn up there. And you would have to add the changes in the function that you get by changing x and by changing y. And so we use this general formula a lot in physical chemistry. Okay, so you might have, let's suppose you have the Gibbs free energy, depends on moles of A, moles of B, temperature, and pressure. You would be able to say, okay, the change in the Gibbs free energy is the partial derivative with respect to Na times the change in the moles of A. plus if you change moles of two things, we'll have a derivative with respect to that. And then you will have the change if the pressure is changing. And if the temperature is changing. And if we're only interested in how the free energy changes with the temperature, we can sort of ignore all of these terms and just look at this one. Or if we're interested in how does the Gibbs free energy change with amount of A and B, we would look at these two terms and ignore the other ones, say constant pressure and temperature. But this is an important, concept to learn about, like why, where does this equation come from? I think when I was taking PChem, I don't know when it hit me. It might have taken a while to sink in. Okay, so think about it if you have time. So if I take a look now, let's go to problem. Hold on a minute. So if we go, here's problem 3. Okay, so here we're looking at pressure as a function of volume and temperature. And we use the ideal gas law, nRT over V. Okay, so what's dP, dV? Well, I treat these as constants. So it's basically going to be nRT times the derivative with respect to volume of 1 over V, which is negative 1 over V squared. So this is nRT times negative 1 over V squared, or minus nRT over V. How do I know that the derivative of 1 over V with respect to V is negative 1 over V squared? It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So I just use the quotient rule. Okay. So that's how I get this. This is that derivative, dP dV. What about dP dt? So the derivative of P with respect to T is much easier because it's nRT over V function. So nR over V is just constant. So a constant times the derivative of the function is derivative of constant times a function is a constant times the derivative of the function. The function is T. Derivative of T with respect to T is 1. So this is just nR over V. Okay, so now pressure being a function of volume and temperature, I can write dP as partial P, partial V, dV. So the slope in the V direction multiplied by the change in V plus the slope in the T direction times the change in T. And then I can just go ahead and plug in, this is what's asked in C. I'm going to do it up here, that I'm just going to plug in the dP dV and the dP dt. So yeah, it's a little silly here because I can calculate the pressure at any volume and temperature. But if I didn't know exactly the functional form, but I knew the derivatives with respect to the different variables, I can multiply each derivative by the change in that variable, sum it up over all the variables, and that gives me the change in the function. And so this is something that we use a lot in PChem is dealing with figuring out how to figure out the change, the differential of a function by looking at these contributions from the slopes multiplied by the changes in the different variables.